Glue. In this video, I was going to talk about calculating the number of unique possible key combinations for Pagoda style locks. One of my friends from college was online tonight. He's a really smart guy. He's a graduate student named Alex. We started talking about math problems, and we started looking at like how to calculate the number of combinations of these Pagoda locks. And this is what we came up with. It is late. And so if you see any mistakes in the math, correct us in the comments. So here's what we came up with. So for a Pagoda style lock, where P is the number of free positions a disk can move to, and D is the number of disks in the lock, then F of P is equal to the number of unique possible combinations. And so I just want to clarify too, number of free positions a disk can move to does not include the position the disk is currently in. So for one disk, the number of unique possible combinations is P plus 1. So if there was 9 spaces the disk can move to, plus the space the disk is actually in, 10 combinations. For 2 disks, you get P plus 1 times P plus 2 over 2. For 3 disks, we get P cubed plus 6P squared plus 11P plus 6 over 6. And then for 4 disks, we get the summation from 1 to P plus 1 of I times F3, so taking this equation and putting it here, where we put P plus 1 minus I in for P. We didn't come up with anything for how to calculate these where D is not a constant. We didn't come up with a function of both D and P. It's late, but if you know how to do that, that would be really cool to see. There very well may be Pagoda style locks out there with more than 4 disks. I don't know how many they go up to, but it would be really cool to see like this equation generalized for any number of disks. So next what I'm going to do is just go through an example looking at the Mindy lock. When I was playing with the Mindy lock, I was suspicious. There might not be a lot of key combinations, and maybe it's something you could even make master keys or tryout keys for. So I was curious to do the math for that. Here's the cylinder inside the Mindy lock, and you can see the 3 disks there. And so when I measure it, I measure the space from here to here. That gave me 12 millimeters. But the disk can't actually move that whole space. If I hold it like that, you can see it's limited. There's some bumps on this metal here, and the rear disc is actually bent a little bit so that it can't touch this back end cap. So you don't have that full 12 millimeters available to you. It's closer to 8 millimeters. We don't actually know what the manufacturing tolerances are of the lock. If we just go by their advertising, sort of shooting in the dark, we see something here that says, not feasible to rotate even if the slot's dimension error is within 0.1 millimeter. So if we guess that their tolerances are within 0.1 millimeter, and then we say that we've got 8 millimeters of free position area. Let me show another one first. Here we go, sorry. So yeah, 0.1 millimeter tolerance. At 8 millimeters gives us 80 positions. So if we plug that in for F3, you can sort of see the math here. And the number I got was 91,881 combinations, if that 0.1 millimeter is the tolerance. I was curious what it might look like if we tried some other values. So I went ahead and did 1 millimeter tolerance, where we only have 8 possible positions. You can see going through the math again. In this case, we get 165 combinations, a much smaller number. But at 165 combinations, I think it's, this is still a large enough number. Most people aren't going to want to try to buy a master key set or a tryout key set of 165 combinations. I guess the one other thing I'd like to go over on this too, that makes this one a little bit different, is that this end cap here, if you see that sort of rectangular groove cut in right in the middle, that fits the key. The very tip of the key right there fits in there. And it acts like warding, and that it rotates different amount of degrees for different locks. It's not an ideal security feature because the user can file down this, and then that warding is no longer effective. It's not required to unlock the lock because you can also tension it from the front with the wings higher up. So what this means is that the user can file away the key and gain more access, which is not a good security principle, but just sort of looking at it for a number of key combinations consideration. If we look at the back of it, we can see that it says 3B. I don't know how many different variations of this there are. There might be 100, there might be 20. I have no idea. But what I can say is, we can make some guesses just for curiosity's sake. With 3B, if we assume that there are 3 possible positions for A or B, which is just a shot in the dark, we'll get 6 possible warding combinations. So this gives us 6 times 165 gives us about 1,000, where 6 times 90,000 would give us about 500,000. So extremely large range there without knowing more about their manufacturing tolerances. It may be possible to reverse engineer if you had a large enough set of these locks, but I'm not sure how you would do that. And it would still take quite a bit of locks, I imagine, to see those patterns. But this gives you a general idea of how you can calculate it, and if you do have those tolerances, you could get a much better number. Anyways, that's it. Yeah, thanks for watching.